we've talked about sources producing potential differences between points in space. And we defined VB minus VA in terms of the integral of the electric field of the source as we go from A to B. But how do we calculate this? We've seen that for symmetric distributions where we know the electric field, that's possible. But when our distributions are non-symmetric, the Gauss's law won't give us the electric field, and we need another approach. Now, we had an interesting thing for a point charge. If we had a point charge, and we started at infinity, and we ended at a distance r away, it doesn't matter how we got there, where this is a distance r from the source, then we have that the potential difference between r and infinity, so that's any point, here's where our A is, and here's where our B is, between these 2 points in space, was given by a very nice function, kq 1 over r. Now, it's this function that's going to be the starting point for a superposition principle. But first, what we'd like to do is choose a 0 point for our potential. And you can see there's a very natural place to choose a 0 point, so we're going to choose our potential at infinity to be 0. Sometimes in electrical engineering, the 0 point is referred to ground, but we'll call the potential at infinity to be 0. And that implies that we have a potential function for a point source, r. Let's always remember that v of infinity is 0. And again, when you see this function, it has a very physical meaning. It's if you take a test charge at infinity, you bring it to a distance r away from the source, you calculate using Coulomb's law, minus the work done, you divide by the test charge. It's precisely what this quantity is. But this begins to be a point, and you can see that if we looked at this function, where QS is positive, and we plotted V versus R, well, at the origin, there's a singularity, and it drops off like that. And when QS is negative, that same function goes to 0 at infinity, but it starts off as negative because the source here will be negative. And so these are our pictures of our potential function. And now what we want to do is we'd like to see what would happen if we have a continuous distribution of charges. How can we exploit this idea for a point charge to get an integral formula?
So what I'd like to do before we proceed, before we go any further, is I'd like to talk a little bit in general terms, and then I'll use a specific example about the superposition principle. This is something which, on the one hand, feels obvious. The superposition principle is something that we use in a way that feels completely natural, and sometimes we don't think about it. But I wanted to pause and to talk about where it comes from and how important it is. How did we first see it? Well, we first saw it at the moment when we introduced 2 charges for the first time. So we had, let's say, a positive charge here and a negative charge here. And we then perhaps asked, what is the force on a test charge here? So let's say I have a little positive charge here, and we asked, what's the force on this? And we then said that the superposition principle tells us that the force on this little test charge is the vector sum of the force due to the interaction with this one, which is a force that pushes it this way, and the interaction with this one, which is a force that pushes it this way. So where did this come from? This cannot be derived. The superposition principle cannot be derived from something that we did earlier, just as Coulomb's law cannot be derived from something that we did earlier. Everything that we've done in 802 so far is built on 2 starting points, Coulomb's law and the superposition principle. Each is equally foundational, fundamental. If this were a math class, we would call them axioms. It's not right to call them axioms here because axioms are human constructions, And these are not human constructions. These come to us from nature. But the reason that we know that Coulomb's law is correct ultimately rests on doing experiments and observing phenomena in the natural world. Same with the superposition principle. And so what we are doing is starting from Coulomb's law and the superposition principle. We're building up consequence upon consequence upon consequence. We're describing more and more and more phenomena. And as we go, we can compare the consequences that we derive from these two starting points. We can compare them to experiments, and that's how we gain confidence in our two starting points. So we've generalized the superposition principle from where we started. The first thing that we did was we switched from talking about forces to fields. So I said that these vectors were the forces on a charge q, but now we know that I could just as well have had no charge here at all and just said that I have some point. This is a point P. There's no charge there. And I'm asking what the electric field is at the point P. And well, the electric field is the vector sum of this electric field. And this electric field is the electric field due to this charge. And this electric field, which is the electric field due to this charge. And the actual true electric field at the point P, this is the point P, and the electric field at the point P is the vector sum of these two. And so, I'm sorry, I just wrote this where I should have drawn the vector. The electric field at the point P is a vector like this. It's the vector sum of the two contributions to the electric field. And that's the superposition principle for electric fields. What's the electric field at the point P? Well, it's the vector sum of the electric field at the point P due to this charge and the electric field at the point P due to this charge. We then did a further generalization, and we started talking about potential energy. So I have electric fields now anywhere on the board. And let's say that I brought some test charge in from infinity along some path to this point P. And when I want to compute the potential energy that that associated with adding this little test charge q to the configuration that I've drawn, what do I have to do? Well, I have to do an integral of the electric field dot ds, where ds walks me along this path. And since this is linear in E, when I do this integral, I can do this integral in two pieces. First, the electric field that I put here can be the electric field due to the green negative charge. I'll do the integral E dot ds for that electric field. Then I'll do a second calculation. I'll do the integral E dot ds, where the E I put in here is the E due to the red positive charge. And then I add the two results, and that will give me the integral of the actual E dot ds because of the superposition principle. So the actual E is the sum of those two contributions. So the actual potential energy is the sum of the two integrals. So superposition applies to potential energy also. And then the last step that we just took, we took potential energy and we divided out the test charge Q. And when we divided out the test charge Q, what we derived was the electrostatic potential. That's what I want to end with. I want to talk about the superposition of electrostatic potentials. And because the potential energy satisfies the superposition principle, how do I go from energy to potential? I just divide out by the test charge. I will still have something that's linear in electric fields. And so superposition applies. So if I want to know what the potential is at a point P, I add up the potential due to this charge and that charge and just add them up. That's superposition as applied to potentials, and it all follows from where we started with the superposition of forces. To make sure that this is clear, I'm going to do a simple problem. I'm going to say that I have three charges. And let's say that I have a negative charge here, and a negative charge here, and a positive charge here. And what I want to do is I want to calculate the potential, the electrostatic potential at a point P, and I'm going to choose this point here. And I want to know what is the electrostatic potential at this point. So to do this, it's convenient to have axes, so let me draw my axes. Here's my x-axis. Here's my y-axis. And let's say that this distance is a, and for simplicity, I'm going to make this distance a, and for even further simplicity, I'll make this distance a also. And now I can sit down and calculate the electrostatic potential at the point P due to these three charges. If I call this one charge 1, and this one charge 2, and this one charge 3, then the superposition principle applied to electrostatic potential tells me that V of P is equal to the sum of three terms. So the sum over I running from 1 to 3 of K, Q, I divided by RIP, where RIP is the distance from charge I to the point P where I'm evaluating the potential. So I can now start writing out these three terms. But before I write out the answer, where did this come from? This came from, this is the superposition associated with principle applied to potential. This came originally from the superposition applied to forces, through the superposition applied to fields, through the superposition applied to energy. OK, so let's go ahead. V of P, sum of three terms. Let's start with term 1. So I have here my charge is negative, so I have a minus KQ. And the distance, RIP, is the distance from this to that. That's root 2 times A. And let me skip to the third term. So I'll write down the middle term in a minute. Let me skip to the third term. The third term coming from the third charge here, well, that charge is positive, so I have plus KQ, same distance, root 2A. And so what I see here is that if this middle charge, if charge number 2 were not there, if I only had charges 1 and 3, then my potential at the point P would be 0. So let's pause for a second. First of all, you might be bothered by the fact that over here I had vectors, and all of a sudden here I have a scalar quantity. This is just a number. This is a number. I'm going to add 3 numbers up. Right now I have 2 numbers written down. I'm just adding up numbers here, no vectors. So the electrostatic potential is a scalar quantity, and yet somehow it's related to these vectors. Well, we saw how it was related by doing this integral in the past, but it somehow feels like there should be a way of getting from the potential back to the electric field. And how can I go from a scalar quantity back to vectors? Well, if all you know is the V at one point, sorry, you can't. A way to understand this is to think back to 801. In 801, we had potential energy. If the potential is at this level, if all I tell you is the potential is at this level, and I have a ball on that potential, well, if the potential is like I'm showing in my hands here, the ball doesn't roll. But if the potential is sloped, then the ball is going to roll. So if all I tell you in 801 is that the potential has this value at this point, I haven't told you whether if I put a ball here it's going to roll or it's going to stand still. So similarly, if all I tell you is that the electrostatic potential here is 0, that doesn't tell you whether if I put a charge here, would it stand still or would it move? Well, let's think about what the actual answer is. We're still supposing charge 2 wasn't there. If I put a little charge there, let's say I put a little positive charge there, it's going to be pulled this way by this charge. It's going to be pushed that way by this charge. There's the net force on it is going to be in this direction. It will not stand still, which is to say that there is an electric field here, even though the potential is 0. And this electric field must be related to the slope of the potential, because the electric field is telling the charge to go this way, and that the fact that the charge is going this way must be related to a potential being sloped. So what we're going to learn is that the way you go from potential back to vectors involves looking at the slope of this scalar function. But for right here, let me just end by finishing the problem. I left out charge 2. Let's put it back in. I've got a minus KQ divided by a distance a. And so the answer to the question that I pose, what is the potential at this one point, is it's just minus kq over a. But knowing the answer to this question does not tell me what the direction of the electric field is here. We'll return to that. To learn the electric field here, I have to do a more complicated calculation, which will involve taking a derivative of the potential, not just at one point, but in an entire region, and we'll come back to that later.
Let's now look at some continuous distribution of charge. So here we have is a continuous distribution of charge. And what I'd like to do is to be able to determine the potential difference. Now, I'm going to consider this to be infinity, where I'm choosing a 0 for my potential, and the potential difference at some point p between these 2 points. So what I want to look at is the potential difference between p and infinity due to this continuous source of charge. Now, recall that amounts to taking a test charge from infinity, moving it to p, calculating minus the work done, and dividing by the test charge. But we've already done that in the following way. Imagine that we divide the source up into small pieces, dqs. And this small piece is a distance r dq from the source to the point p. So that's that distance there. Then for just that test charge already, we've calculated this integral. We know that we've calculated by looking at point charges that this is just dqs over the distance from dqs to p with a constant k. And this comes from just treating this as a point charge. Now, remember, here we have that v of infinity is 0. And now when we want to calculate the entire potential difference between infinity and r, all we're going to do is add up the effect of all these source charges. The distance r's can certainly change for these various elements, and what we get is a continuous integral, vp. Now, again, all of this is implicit with infinity of the integral over the source of k dq source divided by the distance that that source element is from the field point. And this is a result that we can use to calculate the potential difference between infinity and p. And it's a little bit tricky to figure out how to do that, but we'll now look at this in a particular coordinate system to help us. So let's do something like this. Let's choose an arbitrary origin here. Let's write our little dq element here. Our source can be complicated. This is the source. Here's our field point p here. And what we'd like to do is introduce a vector, r, to the field point. That's from the origin to the field point. And we'd like to introduce an integration variable, vector, r prime, that goes from the origin to the source. I'll write r prime source. And this distance, rp minus r source prime, is the distance that dqp, the source is from p, and we see that the magnitude of that vector, rp minus r source prime, is in fact the distance r dq sp. And that's the quantity we want. So now using our 0 point, we can write the potential function at the field point. That's the field point. And we'll make this a little vector. This is a scalar function, but the field point is the position of that point. That's equal to the integral over the source of k dq source over the magnitude of the vector, the field point vector, to the source vector. And this is a tool that we'll use to calculate potential functions for continuous distributions. Let's calculate the potential for a continuous charge distribution. And the distribution we're going to look at is a ring. So here we have a ring of radius r, and the ring has a total charge q that's distributed uniformly on the ring. Now, let's in particular look at, here's infinity, where v of infinity is 0. And let's consider a point P that's a height z above the ring. And what we're after is the potential function at the point z. This is what we call the field point, minus infinity. That's the potential difference. But remember, we've chosen that to be 0. And that's our integral now over k dq source over the distance r dq source p. And this is an integral over the ring. Now, we can do this function, we can do this integral a couple of different ways. But first, key point is to choose a source. And I'm going to pick my source over here, dqs. And remember, the key distance here was the distance from dqs to where our field point is, P. And in the geometry of this problem, we can see immediately, without anything special, that this distance, P, is equal to z squared plus r squared to the 1/2. And now that's going to produce a potential function. And we can write our integral now as v on this axis z is equal to the integral over the ring of k dqs over z squared plus r squared to the 1/2. Remember, potential function is a scalar. It's not a vector. Now, as we go around the ring, what is our integral? Well, we're just adding up all these pieces as we go around the ring. And notice that every part of the ring is the same distance to the field point. So the quantities in this integral, k and the denominator, pull out of the integral. And we have k over z squared plus r squared to the 1/2 integral of dqs over the ring. And now, what does this integral mean? We're just adding up the charge as we go around the ring. And that's simply the total charge on the ring. So we have the result kq over z squared plus r squared to the 1/2. And that is the potential function for the ring along the axis. Now, there's a lot of things we can look at right now. The first thing we want to do is let's imagine the limit in which z goes to infinity. So we're going very far away. Well, let's look at it this way, rather. Instead of z goes to infinity, we want to just look very far away from the ring. So our variable z is much, much bigger than r. Then what I'd like to do is write this potential function. I'm going to pull out the z, and I get 1 plus r over z squared to the 1/2. And I can use my expansion of the denominator to write this as kq over z times 1 minus 1/2 r squared over z squared plus higher order terms. And we can see that in the limit, as z is much bigger than r, this term goes to 0. We have a constant. And our result is kq over z, which is exactly what we expect. Because if we're very far away, this entire ring looks like a point charge, and we're a distance z away from it. And that's the potential function for a point charge, where the point P is a distance z away. So there is a nice calculation for the continuous distribution using our integral superposition principle for potential functions. let's calculate the potential at a point P where we have a finite rod of a charge density lambda, uniform, and I'm going to place a point P here at the end. And remember, out here, this is infinity, and I'm choosing my 0 to be at infinity. And I want to calculate v of p minus v of infinity, which is 0, using our formula for the potential, the superposition principle, where we do k dqs over the distance rs to the point P, integrated over this short rod. Now, once again, the key to all of these calculations is to choose a coordinate system. And I can choose a coordinate system a variety of different ways. I could pick my origin at the center of the rod. I could put my origin here at the end. I'm just going to choose my origin out here. I'm going to call this x equals 0 at the end. And now I want to try to show you another way that we've written this, just so that you can see it. I'm going to pick a little element dqs right there. And we wrote this as k dqs, a field point vector, minus a source vector that was our integration vector. And let's just draw those out so you can see what they are. So this is a vector from the origin to the field point. I had to displace it a little. And this is the vector from the origin r, s. And now I can continue my coordinate system if I choose this to be my positive y-axis. Now remember, we're only taking magnitudes, so we'll use vectors, but we'll take magnitudes at the end. I write my field vector as the position x of the field point I hat, where this distance is xp, going from the origin to there. So here we are at xp. And here's the key thing. My integration variable, I'm going to write as x prime I hat, where this distance is x prime. And so rp minus rs prime is just the magnitude. Now what we have is simply xp minus x prime. And so that's how I've expressed the denominator. Now the dqs, this again, remember, x prime is the integration variable. And so I need to express, just like we did with Coulomb's law, the small charge here in terms of the integration variable. And what I can do is I can call this distance dx prime, and then the amount of charge that's on this small element is the charge density lambda times dx prime. Now, often, sometimes people will write this as lambda dl, and that's true abstractly, but it isn't relating to our integration variable. So we don't want to do that. We want to write our dq in terms of the integration variable. And now you can see why, because that the potential at the field point minus our 0 at infinity is the integral over this rod. And what are we integrating our integration variable from? Well, we're just taking little pieces. And by the way, that's why we choose dqs at some arbitrary point. We don't choose it at the origin, because then x prime would be 0, and we couldn't set this up. And we're integrating x prime, our integration variable, from 0 out to the end of the rod. And let's say the rod is length L. So we integrate out to L. And now we can use our results. We have lambda dx prime over xp minus x prime. And here's an integral that's very straightforward to do. It's equal to minus k lambda, the natural log of xp minus x prime, evaluated from x prime equals 0 to x prime equals L. And when we put those two pieces in, we have the natural log of xp minus L over xp. And if I want to flip this, I get k lambda of xp over xp minus L. And this potential difference, depending, we've missed a lambda here, have to be careful. So let's get our lambda outside. And this quantity will be positive or negative depending on the sign of lambda. For lambda positive, we see that this quantity is greater than 1, so the log is positive. So the potential at our field point, xp, is positive. So for this positive charge, that's a positive point. And when lambda is less than 0, the potential there will be negative. And now that we have our potential function, we can use, if we wanted to move charges anywhere in the presence of this rod along the x-axis, we can use conservation of energy. And you should try that problem out yourself.